Would you say that we live in a non-equilibrium world, Amy?
Yes, non-equilibrium systems are all around us.
Yeah, we're part of the PaCER collaboration called VISCOUS. We're aiming to model fluid flow at the atomic level using high-performance computing resources at the Pawsey Centre. My name is Dr. Emily Carl. I'm a scientific programmer at the Australian Institute for Bioengineering and Nanotechnology at the University of Queensland in Brisbane, Australia.
Okay, my name is Dr. Amy Geddes and I also work at the Australian Institute for Bioengineering and Nanotechnology at UQ, and I work on molecular dynamics simulations. In our group, we're working on improving filtration membranes, for example, for desalination and water reclamation. There's also a lot of work on batteries in our group, so for energy storage and safer battery technology in the future.
Our project really is focused on statistical physics, and we're interested in modeling what we call non-equilibrium systems. So anytime we have a system where there is some net flow or net flux, as physicists say, whether it be a flow of particles like fluid flow in water, or whether it be a flow of electrical charge or heat, that system is out of equilibrium or non-equilibrium. These systems are really quite difficult to model, not just because we require lots of computational resources, but because the science is still evolving. It's not very well understood. And that's what our project really aims to do. We're trying to bring together both the physics knowledge that we have in our research group with also the computing resources at Pawsey, and hopefully we'll be able to push forwards the state of molecular simulation for non-equilibrium systems. We're hoping that with this collaboration, we can take some of the algorithms that our group has developed and make them more widely available for researchers everywhere. So they're not just siloed off within our institute, but really we can contribute them to widely used, public, and importantly open source code bases so that they can be of use to the wider scientific community.
And PaCER, the PaCER project has been extremely helpful in us achieving these goals, mainly because we've been introduced to a wide network of high-performance computing experts.
It's been fantastic being able to work so closely with people from the infrastructure provision side at the Pawsey Centre. We've been able to get that real deep breadth of expertise and make sure that our codes not just work, but work really, really well, and that we'll be able to scale them up to any size system that we want to simulate, whether it be a really small one or a really, really large system like a water filtration. When we say large systems, we don't mean physically large, like big. We mean, they might have hundreds of millions or more atoms in them, but typically we're only interested in sort of nanoscale systems, a couple of nanometers on the side.
Yeah, computationally large.
Yes, exactly. And that's the thing with this sort of computational physics, right, is often even to get really, really microscopically sized systems, we need a lot of compute power to get any kind of insight into what's going on with them. And the benefit of Setonix is that, and of PaCER as a development program, is it has a lot of graphics processing units. And these GPUs, which are sort of similar to the things that you would have in your computer at home for playing video games or doing video encoding, they're extremely powerful computational hardware, but they require special codes to use effectively. And our PaCER collaboration has given us both the resources and the connections with the expertise to make sure that we can use those to their fullest potential.